Okay, today I thought that we'd do something maybe a little bit different and try to bring in a little bit of the mechanics that you might see after a good amount of kinematics and projectile motion. And this is looking at the torque that is exerted on a projectile in standard projectile motion due to gravity about its launch point. I want to do a couple things here. First off, we'll calculate the torque of gravity about this launch point. We'll also calculate the angular momentum that the particle has as it moves along this projectile, again, with respect to that origin, the launch point. And then we'll check to see whether or not Newton's second law for rotation holds. It should, and it does, but we'll double check. I want to show that the net torque that's acting on this system is equal to the rate of change of the angular momentum. Now, as a quick reminder, the torque, which I'm calling tau here, vector quantity, which is made of the cross product of the position of your object, in this case, our point projectile, and whatever forces are acting on it. There's only one force acting on it here. That's the force of gravity. We can also define the angular momentum of this point particle as its position vector cross its momentum vector. So let's go ahead and calculate these things out and see what holds. First off, notice that we can always write the position vector as just x in the horizontal direction, I'll call that I hat, plus y in the vertical direction, I'll call that j hat. There is no z component here. And we know what these x and y components are from kinematics. So I'll go ahead and write those down. We've done that before. Okay, so in the x direction, we're starting everything at the origin here, so we only have that linear term, no acceleration in the horizontal direction. So v naught x is the initial x component of the velocity. We could rewrite that in terms of v naught and cosine, but let's just leave it like this for now. And of course, it will evolve according to time, horizontally, linearly. The y component does have the same sort of term depending on the initial y velocity, and then it has that acceleration term that we're so used to downwards. Okay, that's pretty easy. Another thing we'll need is p, the momentum. Now let's recall that the momentum, at least of this non-relativistic point particle, will just be its mass times its velocity. And of course, the velocity vector is the time derivative of the position vector. So we can write that down pretty easily too. Okay, so the x component, of course, is a constant. The y component does decrease or become more negative with time because of the acceleration. And then we just tacked a mass on at the front. Hopefully that's not going to matter, but we can be consistent here. That gives us r and p. We could quickly calculate L. Let's do one last thing, of course, which is what is the force? Now, of course, this is the easiest one. The force for an object moving with no drag, uniform gravitational field, etc., is just going to be the gravitational force pointing straight down. And again, j hat is the vertical direction. The negative sign points it down. Now we can start doing our cross products here. The reason I wrote it in this unit vector notation is it's very easy to do cross products of Cartesian unit vectors, so we'll just do those as we go. To calculate the torque, I'm going to take my first equation and cross it with the force component. Now, one thing to remember is that any vector cross itself is zero. That's because the cross product is anti-commutative. So this second term that's got a j hat in it, crossed with the j hat in f, will give me 0. So I don't even have to write down that bit. That's just going to leave me this first term with the I hat cross this second, the force term. Okay. Most of this stuff is either a constant, or if not a constant, it's a scalar, independent of vector direction. So I'm going to have a v naught x, a t, an m, a g, a negative sign, and the cross product I hat cross j hat. Now, your right-hand rule can let you figure that out. I hat comes first in the cross product, so take the fingers of your right hand, point them to the right. That's the I hat direction. J hat is upwards, so bend your fingers upwards of your right hand again, and your thumb will point in the direction of the cross product, which in this case is out of the board towards you, and we call that k hat. That's the positive z direction. There is a minus sign that's already in there, so I'll leave that minus sign there, but I hat cross j hat will just give me a z hat. Or k hat. So there it is. There's the torque. Notice it's in the negative k hat direction. It starts at 0, because obviously my particle starts at the origin. And then as it gets further and further out, we notice that lever arm gets longer and longer, so this gravitational torque increases with time, well, in a negative direction, but it increases its magnitude with time. So it's not a constant torque, but it's a pretty easy expression. Okay, now let's calculate the angular momentum, and we'll see if Newton's second law holds. All right, like before, I know that I'm going to have these two terms that I'm going to have to cross together. The cross products of any vector directions with themselves will give me 0. So when I do this cross product, I'll have an I hat cross I hat term, which is 0. I'll also have a j hat cross j hat term, which is 0, but I will have the two cross terms. So I'll start by just writing out those two terms. Let's see. We'll have this term cross the j term here. Don't forget there's still an m on the outside. The I hat cross I hat already canceled. And then I'll have this term, which will have j hat cross I hat. Keep the order as is. Okay, remember the anti-commutativity of the cross product, so order matters. Okay, and then there'll be a j hat cross j hat term, which thankfully cancels out, because otherwise I'd have to square out a binomial, which I don't want to do. Okay, so let's collect our terms. From our first term here, we'll have, well, this v naught xt, the mass, and the v naught y minus gt that came from the velocity. All of that is a scalar, so I'll pull that to the front. And then we have the cross product I hat cross j hat. We already did that one. We know that's in the k hat direction. For the second term, again, the mass and this constant initial x speed, those come to the front. All of this stuff is not a constant, but it is a scalar, so that can all come to the front. And then I'll be left with j hat cross I hat. So let me write these first. J hat cross I hat, we could do a couple ways. We can either just say, well, the cross product is anti-commutative. If I hat cross j hat is k hat, then j hat cross I hat is negative k hat. Or you can always pull out your right-hand rule. So now I start with j hat, that's up. So fingers go up, curl it towards the direction of I hat, which is horizontal. And notice that now my thumb is pointing away from you into the board. That's the negative k hat direction. Okay, now let's see if we can combine anything here. They both have an m out front. They both have a v naught x out front, so those are a common term. And then notice that I'll have a v naught yt k hat minus v naught yt k hat. Those terms will actually cancel out because of the negative sign on that anti-commutation. The other thing we need is to recognize that I have a t times a negative gt, so negative altogether, and then I have a negative negative is a positive, but there's a 1/2. So these don't cancel, but they do combine. So I'll have a positive 1/2 gt squared stuff minus 1 gt squared stuff. So my overall result will be negative minus 1/2 m v naught x, and then I'll put a gt squared at the end like that. And it's in the k hat direction. So the angular momentum is in the negative k hat direction. That's not too surprising either. As this thing curls away from the origin, it's more or less turning, if you want to call it that, in the clockwise direction, which would be a negative component of the angular momentum. Okay, so let's bring these up to the top, and then we'll finish by checking Newton's second law. Okay, so we have our torque. This is the net torque, actually. There's only one force acting. And we have the angular momentum. Now we want to check Newton's second law. for rotation to see if the net torque is the rate of change of angular momentum. Remember that this is like the F equals ma for rotation, although it's beefed up a little bit. It doesn't have the angular acceleration here. It's the time derivative of the angular momentum. We could do this with angular acceleration too if you want, but I think this is easier. So this is pretty easy. Let's just check if the time derivative of L equals the net torque. Well, all of these things are constants. The only thing that depends on time is t squared. Taking its derivative will bring the 2 down, giving us 1. And we still have the negative sign. And sure enough, this is exactly equal to our net torque. So we have verified that Newton's second law does, for rotation, hold for a projectile under the influence of gravity, as we would kind of expect. There are no external torques beyond gravity acting on the system, so nothing else will change its angular momentum. QED.